Right, so we know a little bit about redox reactions. We know how to recognize them. We know what an oxidizing agent is and a reducing agent, although we'll review those concepts in a minute. What we want to know is how do we predict whether or not a reaction will be spontaneous or not. So a couple of reminders. Number one, the spontaneous reaction is one that will proceed without a constant input of energy. So every reaction, or at least most reactions, requires some kind of starting energy. We called that activation energy in a previous unit. We can ignore that. Once that reaction is going, does it continue on its own without a constant input of energy? If the answer is yes, then it's spontaneous. If not, it's a not spontaneous reaction. Second thing we need to know is, or need to be reminded of, is if I write a reaction like this and I write the reverse reaction, and if I look at those, hopefully you can see that those are the reverse of each other. If the question was, are both of those reactions possible? Well, the answer is yes, both reactions are possible. I'm not doing anything too crazy with those reactions. But are both reactions spontaneous? And the answer is no. If one reaction is spontaneous, then the other one will be not spontaneous. Or if the other way around, if I find out that one combination does not give me a result, does not give me any products, I can be confident that the reverse direction would. So our question today is, how do I predict? Well, I have a tool from one time earlier, and that was the activity series of metals. Most activity series that we've seen have not been particularly complete, haven't gotten all the metals in there. But generally speaking, the way the activity series works is the more reactive metal is higher up, and then it will displace or kick out of a compound a less reactive metal or less active metal, as you'll sometimes hear the phraseology. So in the case of the reaction we were looking at before, magnesium being higher up is more reactive. That means it takes the reacted form. So that bottom reaction of magnesium pushing zinc out of the compound and taking its place in the compound, that is the spontaneous direction of that reaction, or that is the reaction that is spontaneous. Okay, a couple more terms. Oxidizing agent, reducing agent, and I'm not really going to say much about them other than the oxidizing agent causes oxidation. How does that happen? And the reducing agent causes reduction. And it always feels a little bit backwards because we learn first how to recognize what has been oxidized and what has been reduced, and we generally don't think about the thing that is causing it. However, that's going to be our focus as we move forward, is identifying the agents. Okay, question is going to look something like this. The wording will adjust a little bit. I'll show you another one in a couple of minutes. Here it says relative strengths of reducing agents. That's going to be my focus. However, I need you to understand that if you can think it through better with looking at things as oxidizing agents, that's fine. I'm not going to specify going from the strongest to the weakest or from the weakest to the strongest. I will let you decide. As long as you identify and label it, I'm going to be happy, because it's the thought process that's much more important than the particular nuances of any one given question. So if you had these two reactions, now in that you've got 3 different metals to be paying attention to. So my list of metals is going to be 3 things long, and I need to rank them in order of whatever, increasing or decreasing, but I'm going to be looking at the strengths of the reducing agents. The reducing agents are the things that cause reduction. So I'm going to look at each reaction individually, and I want to break it down into a little bit of detail. Now understand that what I'm about to write is the thought process, not what I expect you to write. We'll talk about what would be expected for me to see on your paper in a little bit. So in the first reaction, where copper ion is reacting with lead metal, that reaction is spontaneous because I'm showing products. Copper ion is being reduced and lead metal is being oxidized. Now, if I look at these things in terms of the agents, that means that copper ion is reducing lead and lead metal is, sorry, I take that back. Copper ion is oxidizing lead and lead metal is reducing copper. That makes copper the stronger oxidizing agent than lead, because copper is the one that's causing the oxidation. So lead is being oxidized, not copper. That makes copper a stronger oxidizing agent. And then conversely, lead would then be, Pb is then a stronger reducing agent. If I take a look at the second reaction where I've had no products, that means that reaction is not spontaneous as written. But what it also means is that the reverse direction would be spontaneous. So as it stands, iron cannot oxidize lead. That's what I'm asking it to do because it's too weak of a oxidizing agent. Where lead, in turn, cannot reduce iron ions because it is too weak of a reducing agent. But as I said, the reverse direction would be possible. Not only possible, but also spontaneous. So if I look at that reaction and analyze what's happening in it, even if I didn't actually observe it, I know it will be spontaneous. And I know that lead ions will oxidize iron atoms, and iron atoms will reduce lead ions. So now I can gauge the strengths of the oxidizing agents and reducing agents within that reaction, that lead ions are a stronger oxidizing agent and that iron is a stronger reducing agent. Okay, put all of that together and just pull out the summary bits from that. I know that lead is going to reduce copper ions. I know that iron is going to reduce lead ions. So there's my three things in a brief little summary. If I rank them in order of strongest to weakest, reducing agents, the strongest one is iron because iron reduces lead, lead in turn reduces copper. So iron must be the strongest reducing agent, followed by lead because it reduces copper but it cannot reduce iron, and copper doesn't reduce anything in this example, so it's going to be the weakest as a reducing agent goes. Okay, hopefully that made sense. And again, all of that, 2 pages of writing trying to analyze what was going on in each reaction, none of that is really necessary for me to see, but it is the thought process that you need to go through. Maybe not in that level of detail, but at some point or at some level, you do need to analyze who reduces whom and get some sort of order going. Okay, we're going to take the same idea, we're going to go a little bit larger, and we're going to get 3 reactions. Similar kind of thing, more stuff going on, more elements involved, reactions that are not spontaneous as written, and all the rest. So I'm going to do the same thing. I'm going to break it down. It's not going to be to the level of detail that the first one was, but it's still going to be more detailed than I would need to see. So I'm going to take that first reaction. By the way, the balancing numbers are irrelevant. The balancing numbers here are just so that I have all my charge balanced as well. But if you didn't, it's not really going to cause any problems. It doesn't change whether or not the reaction is spontaneous. So I know that the, cobalt? Cobalt is going to take electrons away from indium. In is indium. It's not one we use very often, so I'll use indium and In back and forth so you get used to it. So it oxidizes indium. That makes cobalt ion a stronger oxidizing agent than indium would be. And I've got the charge up there, but again, it doesn't really matter all that much. Copper, in turn, will oxidize cobalt, and that makes copper ion a stronger oxidizing agent than cobalt is. So I've got cobalt as an oxidizing agent, and I've got copper as an oxidizing agent, and copper is a bit stronger than cobalt so far. And then I've got copper ion and palladium, Pd is palladium, no reaction. That means that copper cannot oxidize palladium. That means that the reverse direction, where palladium, and you might not know the charge on palladium, that's okay, I didn't either, I just made that up for convenience sake, that reaction would be spontaneous. And as a spontaneous reaction, that means that palladium ion would oxidize the copper. Okay? So now what I can do is I can jump to my summary, and that's cobalt, takes electrons away from indium, copper takes away electrons from cobalt, palladium would take away electrons from copper. And if I put them in order in terms of which oxidizes which, then I have this. And then to put them in an order as oxidizing agents, this time I'm focusing on the ions first. Again, it doesn't really matter. The thought process is the same. I chose to go with oxidizing agents rather than reducing agents. But again, if you tell me what you're doing and you do it, I'm good with that. So palladium is a stronger oxidizing agent than copper, which is a stronger oxidizing agent than cobalt, which is a stronger oxidizing agent than indium, all in ion form. If I did want to look at the metals, if you found that better, then I would do kind of the same thing. I would identify what's happening in each reaction based on the metal, and then I would focus on that. And again, without going through the whole thing, but not talking through the whole thing, exactly the same thing could be said, except now I'm focusing on the metals that are losing electrons, that are giving electrons away, the metals that are reducing the ions. And if I summarized it, copper reduces palladium, cobalt reduces copper, and indium reduces cobalt, unless I can't read what I'm writing. And then I have the reducing agents. Now you'll notice that the reducing agent order is exactly opposite of the oxidizing agent order, which should make sense. Okay, a couple things that before we go. Number one is that I would only expect the one list, and I wouldn't care if you gave me strongest to weakest or weakest to strongest, oxidizing agent, reducing agent, you pick, as long as you label what you're telling me you're doing, as long as you tell me what you're doing, I guess, then I will be good with that. If you mislabel it, that's a problem, but as long as you label it, you tell me that you know what you're doing, I'll take it. And then this is what we should be able to accomplish at this point. Anyway, hope to see you soon. Thank you for watching.